Quad in the back there. So this is the thesis defense for Tanner, evaluating ramp meter wait time in Utah. So just give you kind of a quick overview of how this is going to work. We will start with an opening prayer and kind of through the air in the lab. I invited Corey to do that. So we'll have him give the prayer here in a minute. Then we'll, after the prayer, we'll let Tanner introduce the guests that are here. We also have some people on Zoom. We don't need to introduce them, but just there are just maybe who's on there. Just to tell us who's there. Then we'll do.
You may want to plug in that. So now there's a little round
one there. It's Bluetooth though, so you'll have to connect with Bluetooth.
I can hook it up quick.
USB is just power for it. Power up, so maybe it'll let me do it that way too.
There you go.
Does it work?
There you go.
Okay.
Okay. Yeah, then, well, why don't let's go to that point. Let's just have Corey give us our prayer, then Tanner can introduce everyone, and then I'll let you know where we'll go from there.
Our Father in heaven, we are grateful for this day, thankful for this setting that we're in, that we have to learn academically and increase our knowledge. We're thankful for all the people that have worked so hard for this day, for everyone who has prepared to help Tanner receive this education. We're thankful for his family and for everything that they have done to support him, and thankful for all the professors here at Brigham University who have taken the time to educate and to mentor. We thank you for all the opportunities that we have to learn, and we ask you to help us to use what we learned today and use it as an example to further our studies and to better understand the world around us. And these things we pray again in Jesus' name.
Amen. All right, now why don't you introduce who you got here?
Sure. So on the end is my wife, Tristan, the only girl in the room. And then we have Sam, Bruce, Daniel, Adam, and Corey. They're all students here, and they work in the transportation lab with me. Corey, in particular, was on this project for at least half of it, and so he was really helpful in getting all the data collection done and helping work through that. So that's everyone here, and then online I have some of my family, at least right now, my sister and brother-in-law. So then this is Dr. Williams, Dr. McFarland, and Dr. Schultz. I think all of you, except maybe Tristan, know all of them already.
She's just heard horror stories.
All good things, all good things.
I invited her to my house, so she, you know, somewhat of a big part there. All right, well, thank you. So we're gonna have Tanner give his presentation. During the presentation, the guests are not allowed to ask questions, but you're welcome to keep all your questions for when Tanner comes back to the lab. You can ask them all the questions you want at that point. As far as committee members, if you have a question, something that needs to be clarified, you can ask that. Otherwise, we'll keep our questions mostly till the end, and so when he's done presenting, we'll invite all the people on the sidewall to leave, and the fun will begin. So, Tanner, go ahead.
All right, awesome. So welcome to my thesis defense on evaluating ramp meter wait time in Utah. I appreciate all of you, first of all, for being here and for the role that you've each played in helping me get to this point. Okay, I guess it decided to stop working. There we go. Okay. Yeah. So just wanted to give a quick outline of what this presentation will look like. So going to start off with an introduction about what this project was about, the purpose behind it, and what the existing methods were before this project began for evaluating ramp meter wait time, and then talk about what we did for data collection and the methods we used to analyze that data, and then a discussion on our results and conclusion. Okay, so ramp metering has been used since about the 1950s, and so it's not a new thing, but ramp meter wait time analysis hasn't really been done much at all. And the Utah Department of Transportation has become concerned about ramp meter delays on the ramps, particularly because of ramp metering. And so their goal was to be able to provide estimates of wait time at these ramps so the public could be aware. And so along with that, the purpose was to be able to assess that data and use the existing detection systems that were on the ramp, so they wouldn't need to use new technology, and use that data that they get to assess the wait times. And this figure shows the span of the areas that are that do have metering along I-15 in Utah. And so that ranges from Layton in Davis County all the way down to Springville. And so right now, what had been done was they had developed 14 different ramps that had predicted wait times while they were being metered. And it was done on a 3-tier kind of broad scale of estimated wait times. And that was below average, average, and above average. And the way that they calculated those was by figuring out the number or the percent of time that the detectors were covered by a vehicle on the ramp. And then they would select an arbitrary value based on manual data collection that would say, for example, in this case, if the occupancy at the middle of the ramp was 8% over that detector, they could say that's going to be 1 3/4 minutes of a wait time. And so it was kind of arbitrary, and it required a lot of manual data collection and calibration, and it couldn't be applied to various ramps. It was very different for each ramp. So what we did for our data collection was we selected 4 different ramps that you can see here, and we tried to space them out and also use different ramps that have just kind of unique characteristics so that we could get a broader range of ramps that were being analyzed. And so we have one in Davis County, which was Layton Parkway, and then we have Pleasant Grove Boulevard, Bangerter Highway, and University Avenue. And so you can kind of see that they are spaced out throughout Utah, Salt Lake, and Davis counties. And they all have unique characteristics in terms of the length of the ramp, the number of lanes on the ramp, and just the general area that they're in.
Was that figure in your thesis?
It is. It may not have been in our first draft that you received, but it.
I downloaded the draft from Brigham. Which I assumed was the very latest.
It's in chapter 3 right now. It should be,
3, so
yeah.
it's not chapter 2 where the other figure is.
Correct.
Oh, never mind, it is.
Okay, good. You made me nervous there. And so we selected those 4 ramps because of, like I said, they just have kind of unique characteristics that would apply to a more broad range of ramps throughout the ones we don't analyze. And then on those ramps, there are 3 different detector locations. And so what we have called those are the excessive queue, which is at the very beginning of the ramp when you get on the ramp. Then you have the intermediate queue about midway through the ramp. And then you have the passage queue, which is located just past the actual ramp meter signal. And so with those 4 ramps, they all also had different times that they were being metered. And we collected the data during the PM metering period. And so it ranged from anywhere beginning at 3:30 all the way until 6:30, depending on which ramp was being used. And so the detector data had volume counts and occupancy counts, which is the percent of time that a car was over the detector. And that is from the detector data. And it also provided the metering rate, which is the amount of vehicles that are being put onto the freeway per minute. And so we were able to use that detector data, and then we collected our own data in counting the number of vehicles coming onto the ramp, leaving onto the freeway, and then the total queue length at the ramp meter signal. And in some select instances for calibration and verification purposes, we also collected the wait time. So the general basis for the methods that we used is called the Kalman filter equation. And there are two parts to it. One is called the state equation, which is sort of a base equation. In this case, it's just at the very beginning here. And it may look a little bit confusing, but it's actually a pretty simple equation. So the beginning part, it just says the number of vehicles on the ramp is equal to the number of vehicles that were on the ramp a minute ago, plus the number of vehicles that came in minus the number of vehicles that came out. And so that's just a basic kind of conservation equation for the number of vehicles coming onto the ramp. But a lot of times, because the detectors aren't very accurate, either one of the detectors could be misaligned in counting the number of vehicles. And so this value of C, which is called a volume balancing ratio, is used to balance the number of vehicles entering and exiting the ramp. And then the second portion, which is called the measurement update, uses other data sources from the detector data, which is the occupancy and other ramp characteristics like the length of the ramp, the length of the vehicles that's estimated to be on the ramp, and the number of lanes of the ramp. And so with those two parts of the equation, we then developed a few different ways to manipulate that equation to predict the queue length. And so the first one, like I said, is the conservation model. And that just assumes that the K value there is 0. And that means that we're only considering the first part of that equation, which is the number of vehicles entering the ramp minus the number of vehicles that exited the ramp. The next one we call the Vigos model. It's named after the author of the person who created that model. And they used micro simulation. So it wasn't actually real field data that they used, but they used micro simulation to predict the optimal K value that could be used to make the best queue length estimates. And through all their estimation, they found that was 0.22. And the value generally ranges between 0 and 1, but throughout all of their estimates, they found the optimal value for the different scenarios they analyzed was 0.22. And then we used an optimized K, which can't be used in real time because it depends on the manual data collection. But what we did was we grouped the data into 15-minute increments, and then we compared the manual data to the estimated data from the equation, and it minimized the root mean squared error between those to find the best K value for each 15-minute period. And then based on that, like I said, since we can't use that in real time without having to have manual data collection, we use those K values to develop linear regression models and a heuristic model that could rely just on real-time data from the detectors. And we'll talk about those in just a little bit as well. So like I said, the conservation model is just that first half of the equation. So it's the simplest one. And ideally, this would be the one that we'd like to use because it requires no calibration, and there's no K value needed. And if the data were perfect in the number of vehicles estimated from entering the ramp and exiting the ramp, if those were equal, this model would be perfect. But from what we saw in our data analysis, the detector data was far from perfect. And so this model was not very useful to us. The VGOS model is that same Kalman filter equation, but as you can see here, it uses 0.22, which was the optimal value they found. And so that was another one that we used. It is relatively simple because you don't have to have multiple K values. You can just plug in that one K value, and that will be used to estimate the Q length at any ramp. And then we had the optimized K value, which, like I said, it uses 15-minute increments to predict the optimized K value for each ramp. And what we found was interesting was that the average K value in those 15-minute periods across all ramps also averaged out to 0.22, just like the VGOS model did. And so based on that optimized K, since we can't use that in real time without having manual data collection, we developed linear regression models. And we had 4 different ones that used the density of vehicles on the ramp, the occupancy at the 3 different locations along each ramp, and also a variable for which ramp was being considered. And based on these results, none of them were all that great. And for example, the R-squared values can range between 0 and 1, with 1 being the best, and all of them were very low. But we didn't necessarily expect them to be great just because of all of the different things involved in these models. But we used this first one in the first column because it did have the highest R-squared values, and it had the lowest negative value for the log likelihood, which is also a way to assess the quality of the estimates. And so this equation kind of just sets forth the way that K would be calculated. And so these values are pulled from right up here, for example. And so K would be calculated with the base value starting at -2.5. And then based on the intermediate Q occupancy, the density in which ramp was being considered, those values would be multiplied and added together based on whatever was happening on the ramp in that minute. So after that, we then made a heuristic model, which is just a way to simply group together the data. And we used a cluster analysis, which groups all of the data into different groups that can be used so that instead of having just 1 K value, we can have 3 K values, and it's based on the occupancy on the ramp. And so we use the passage Q occupancy, which is again at the ramp meter signal, and then the intermediate Q occupancy, which is midway through the ramp, to group together the data. And it created these 3 clusters, one kind of down in this corner with low occupancy for both, and then one with a higher passage Q occupancy and a lower intermediate Q, and then one that has just a higher intermediate Q occupancy. And so that clustering was done automatically based on the centroids of each cluster being created to best estimate the data. So based on that, we had 3 different K values.
Can you go back?
Sure.
You actually did K means on 3D data, right? Not 2D data.
This was just with the 2D data assessing the passage Q versus intermediate
So
Q.
why didn't you use all 3 dimensions?
So the issue with, we could have used the excessive Q, which is that 3rd detector, but a lot of times, especially because our data collection was done midway through COVID, the excessive Q, which is at the very end of the ramp, had really, really low values. And so it wasn't really useful to, it didn't really add anything to.
Well, I'm just thinking for clusters, that might be another cluster when that was occupied.
Yeah, that could be. It was just that the maximum we really ever saw at the excessive Q was never above 10%, and a lot of times it was even closer to 2 or 3%. And so it was kind of just a flat line of excessive Q throughout most of the whole day on each
And what
ramp.
was happening with the other two values when it was occupied?
With the 2 different occupancy locations, those tend to be a lot higher because that's when you're
When you had occupancy at your third one, what were these two?
so the percentages were generally ranged a little bit higher, as you can see here. So sometimes they are close
So
to
you would have a
0%.
group up in that upper right quadrant if you would have the 3D thing?
That is a good question. I'm not sure right now how to answer that. But I guess just the occupancies are calculated based roughly on how busy the ramps are. And so that's what's happening up here is with the higher occupancy values, that's when the vehicles are traveling much more slowly because they
So
can't
it'd
pass
be more
over.
likely that that third one would be occupied.
Yes, yeah, okay, I see what you mean. That would be the case in these upper quadrants, but there are so few data points up there compared to the other locations that, like I said, it was just with the lower volumes, it was definitely much more towards the lower end of the spectrum.
So one other question for you on, because K-means you pick your groups before you run your analysis. Why did you pick 3?
We checked having anywhere between 2 and 7 clusters and
I don't think
3.
that was stated.
I don't know that it was. I can add that in. But 3,
Well, it's, if you check, that's fine.
sure.
It's just you didn't say that. Karen. You
Yeah.
said we chose 3.
Yeah, so we chose the number of clusters that would be used, but with adding in more and more clusters, it just reduced the number of observations per cluster, which could make it less reliable or widely applicable. And so with that, so for example, with this third cluster, even with just 3 clusters, it only had 20 observations. And so the mean K values came out to be 0.189, 0.337, and 0.17. And we had hoped to find some sort of correlation between the K values and the occupancy. For example, if the occupancy was higher, K would be lower or something along those lines, but there was no real correlation that we could see between that. But
So go back to your plot. So blue. So turn everything off below the 45-degree diagonals in the blue group.
It's more right of 15.
yeah, so
Okay, okay, so
Yeah.
right.
Yeah, the
Yes,
values
now
are-
the vertical divider.
yeah, roughly cut off at about 15%, and it's not quite perfect, but it's roughly at about 15% and then about 12 to 13% on the
Well, is
Y.
it? No, it's just 15, you got lots of stuff going all the way down.
So those, I think those points between 10 and 15 are green.
Yeah, so these are all still in this section, and then starting over here, they're in
But
cluster
it goes
3.
all the way down. I mean, you've got a blue point clear down around 8, so it's just almost a vertical dividing.
Right.
Right.
That's right, yeah.
So that third cluster just depends on the IQ occupancy, not on the PQ.
Mhm.
So you do have a relationship between K values.
Yeah,
It's actually low as K.
to some degree, it does make that those clusters based on the occupancy values, but in terms of, if you look at the K values, we have cluster 1 at 0.189 and cluster 3 at 0.17. And so you maybe could say that K values are lower in this kind of
Yeah, so if you have
section and higher up here, but
a Low IQ, high PQ, high K. Everything else is low.
yeah. So it was difficult, and there we wanted to.
I just take
yeah.
it when you said there was no relationship, there's clearly a relationship. That's the whole point of K.
Yeah, and there is to some degree. It's definitely not a linear kind of easy fashion that you'd normally look at it, but
Yeah, but the first and the last groups are very similar, but the second group.
right. And that was what was interesting, because if you look at this value here in red compared to the one right next to it, to have, those are assigned very different values and they're almost essentially equivalent. And so it's
Yeah, but
it's
you're
definitely
assigning
not the
value to
perfect way,
center of
but
the cluster,
right,
not the edges.
right. So looking at the results of all of this analysis then, so based on those equations, this plot is a little bit busy, so I have some simpler ones based on the best model that we saw. But the thicker green line is the actual observed Q length that we saw. And then each of these other lines are the other estimated models. And so you can kind of see that it tends to follow all the sort of peaks and valleys of the Q length throughout the day between 4 and 6:30. But there are also definitely times where it underestimates the actual Q length, or in some cases overestimates the actual Q length.
So any guess on why the model would be biased low? I mean, there are a couple of places where it goes high, very rarely.
Yeah.
It's mostly biased low.
Yeah, generally it does underestimate it, and I'm not 100% sure why that is.
Did you calculate a mean error?
Yes, so we'll see that in just a little bit after these plots. So the it does tend to underestimate it for most periods and most ramps, though. So, oh yeah. Okay, so the original purpose of this project was to estimate wait time, but there weren't any ramp meter wait time algorithms out there yet. And so we used that existing ramp meter Q length algorithm and assessed it that way, but we knew we had to get it into wait time. And so, like I said at the beginning of the presentation, the metering rate is part of the detector data, and that's the number of vehicles that are allowed to enter the freeway per minute. And so it was actually pretty simple. You could just get the wait time by finding the existing queue length and dividing that by the metering rate. And so if you had 40 vehicles on the ramp and a metering rate of 10 vehicles per minute, then that would mean that you could just divide out the vehicles and the vehicles per minute, and you'd get 4 minutes of wait time for that period. And so with that, this plot looks pretty similar to the previous one, just because all it's doing is dividing by the metering rate. But in this case, it is now assessing wait time instead of queue length. And again, like you can see, the general peaks are followed, but it's not a perfect relationship between the observed and the modeled
Okay.
wait times.
So a question. So is the observed wait time that you're showing on this plot, is that the observed queue length divided by the meter rate, or did you actually observe the wait time?
Yeah, so we did assess the wait time on a couple of ramps, and just select days for verification, but this is just the observed queue length divided by the metering rate. And so we assessed that conversion by manually calculating the wait time and observing it to make sure that converting, yes, that's all, it's in chapter 4. I can't remember the number of the figure right now, but we used this equation after we had counted the wait time manually on 2 different ramps to make sure that correlation by dividing out by the metering rate was still useful and viable so that it could be used.
Yeah, but just to be clear, that figure that you're showing on the next slide is not that analysis.
It's not an observed wait time per se, I guess. It's an observed queue length divided by the metering rate. And so, like I said, the general trends are followed here.
Figure 4 stuff.
And so just to simplify the view here, we found that the VGOS model, which used that average value of 0.22, was the best model that we could have to estimate the wait time. And so I have a few plots here that show that by a ramp, what it actually looks like, so it's a bit more clear. And so this is, again, is the observed queue length divided by the wait time in red, or the metering rate in red, and the bluer color is what the VGOS model estimates for the wait time. And so, again, it does generally underestimate it a little bit. There are other periods where it jumps above the observed wait time, but we generally found it was within about 45 seconds of the observed wait time. And so this was at Bangor Highway. Similar trends followed on this one at Layton Parkway. And again, the general trends are followed, and there are some periods where it does not do very well. But the general trends throughout that whole day on all 5 of these that we collected were within about 45 seconds for the most part. So this was one of the more interesting ones to us because there's this huge jump in the wait time in the middle of the metering period, and it was still able to capture that peak. And again, like I said, it's not a perfect resemblance of the observed wait time in this model, but the fact that it is able to capture that huge peak in wait time was really useful and interesting to us. And same thing here with Pleasant Grove. There are periods where it under or overestimates the wait time, but for the most part, the general trends are followed. And so here are the root mean squared error results by ramp.
Did you calculate a mean
No.
error? That'll give you whether you're biased.
Okay, we can look into that.
So not a mean squared error, just a mean error.
Right.
Okay. So in terms of the root mean squared error, that is a way of comparing the actual calculated results compared to the models. The best model, or it was almost identical between the heuristic and the VGOS model. And so in some ways, the heuristic model was actually very slightly better than the VGOS model, but because the VGOS model requires only one parameter, and it wasn't based on the clustering analysis that we did that could be a little bit subjective and not applied to any ramp in Utah, we felt that the VGOS model would be more useful to use, and it's much simpler for application for UDOT. And so just one more thing that we did to kind of verify that these results were viable was we added one more ramp that we had never looked at before. And we calculated we manually counted the wait time throughout this past December. And then we compared it against what the VGOS model would calculate.
This is actually measured wait time, not compute.
Correct. This is an actual wait time. And so just like the other models, it's not perfect, but the general trends that you can see throughout the day of jumping up and down are followed, although it does not perfectly estimate the wait time. And so to conclude, based on all these results, it was difficult in some ways to develop these models because there was almost nothing available in prior research that had been done to predict wait time on ramps. And the ramp signals are very unique compared to normal traffic signals because they turn on and off. And so there is very little research that had been done prior to this to calculate wait time. And on top of that, many of those that had been done required extensive calibration by ramp and even by period. And so they'd have a different K value for AM versus PM. And so this method develops a very simple algorithm that can be applied to any ramp throughout Utah, and it does not require that extensive calibration. And so we looked at it by using a conservation model, a VGOS model, the optimized Kalman filter equation, and various different linear regression models and cluster analysis. And based on what we saw, the VGOS and the heuristic models perform best, and they're almost equivalent. And so because of that and the simplicity of the VGOS model, we felt that that would be best to be used. And those models are generally within about 45 seconds of the wait time. And yeah, like I said, because of its simplicity and its lack of calibration required for UDOT, they could be able to use that on any metered on-ramp with little to no work required. And so for future research possibilities, we would recommend that the VGOS model do be applied to additional metered on-ramps to assess whether it is still viable at other ramps. And on top of that, we saw that the loop detection system throughout Utah could be pretty unreliable at times, and especially comparing the different locations of the detection and how many vehicles they would count. And so it would be recommended to